Hi, I'm Andrew Wilson at New York University, and welcome back to the ICML 2020 tutorial on Bayesian deep learning. This is part 4 on Bayesian model construction and generalization. In this part, we'll consider deep ensembles and their connection with Bayesian marginalization. We'll use this connection to describe MultiSWAG, a procedure which marginalizes within multiple basins of attraction. We'll also consider tempering, prior specification, rethinking generalization, double descent, and width-depth trade-offs. Here we'll return to a function space perspective that we considered in depth in part 2. We have a straight line function with a distribution over its parameters, W0 and W1. We can visualize this induced distribution over functions by sampling from this distribution over parameters and looking at the different straight lines we get with different slopes and intercepts. The gray shade here corresponds to a 95% credible set, and the solid blue line corresponds to the expectation of this distribution over functions. In this diagram here, we have a conceptualization of all possible data sets on the horizontal axis and the marginal likelihood or evidence on the vertical axis, expressed in equation 74. The marginal likelihood is the probability that we would generate a data set if we were to randomly sample from the parameters, the distribution over the parameters of our model. We can see here in equation 74 that the marginal likelihood is what we get when we integrate away these parameters. In the example from the last slide, we're just generating straight lines with different slopes and intercepts. So we're not able to generate many data sets at all, but because the marginal likelihood is a proper normalizable probability density, it'll have to assign a lot of mass to those data sets. Alternatively, we can consider a model like maybe a huge multilayer perceptron with a broad distribution over its parameters, which can generate lots of different data sets, but each with not very much probability. We could alternatively consider a model like a convolutional neural net, which is very flexible, so it can generate all sorts of different data sets, but it has very particular inductive biases like translation equivariance, this idea that if we translate an image, its class label remains unchanged. And so it will give a lot of mass to structured image data sets. In order for a model to generalize, it needs to both have large support, it needs to be very flexible, and it should have good inductive biases, a good distribution of that support. So models like convolutional nets can generalize very effectively on image recognition problems because it supports all sorts of different data sets in this application domain, but it has a good distribution of support through biases like translation equivariance. We should be very careful not to conflate flexibility and complexity. As we were describing in part 2 of the talk, we can have models like Gaussian processes, which are extraordinarily flexible, even universal approximators, but in a sense have very simple inductive biases and can generalize very well on problems with even a small number of data points. In this figure here, in addition to the panel that we considered on the last slide, we look at what happens as these three models are exposed to a given data set. We can see that the model with large support but good inductive biases both contains the ground truth description and is able to contract efficiently around it. The model with truncated support contracts quickly. It's quickly constrained by the available data, but it contracts around an erroneous solution. The model with large support but poor inductive biases that spreads its support too thinly across too many data sets contains the truth, but it doesn't contract very efficiently. At the end of the last part 3, we were considering deep ensembles, and we started to hint at their potential connection with Bayesian marginalization. Recall that the predictive distribution that we want to compute is this integral of our conditional predictive distribution given parameters, weighted by the posterior probabilities of parameters given data. And so we want to, in words, consider every possible setting of the parameters and weight them by their posterior probabilities. Now, this Bayesian approach and the classical approach will be similar when the posterior is very concentrated around a small number of parameters, or when the conditional predictive distribution y given w is not varying a lot, where the posterior distribution w given d has most of its mass. Now, in this top panel here, we have a conceptualization of the posterior distribution for a neural net. Multimodal, lots of global optima. And in the second row, we have a conditional distribution. Now, with a deep neural net, there isn't a lot of functional variability within a single basin of attraction compared to between different basins of attraction. So we can see that conceptualized in this second row, where we see that P of y given w doesn't change very much within a basin, but it changes a lot between the basins. In the bottom row here, we're thinking about estimating this integral as an active learning problem. We've observed a single solution, say an SGD solution here in one of the basins, and we're seeing where we need to move in weight space to decrease the distance between our approximate predictive distribution and the exact predictive distribution, the exact answer to this integral. And we can see that we would benefit a lot more by moving to a new basin than continuing to query points within the same basin. And so, indeed, a lot of approaches to Bayesian marginalization focus their efforts just on a single basin. They do Gaussian approximate posteriors. But in deep learning, if we view this integration problem as really an active learning problem rather than through the lens of simple Monte Carlo, then it's very advantageous, given finite computational resources, to do something like deep ensembles and just select points from different basins, and we'll get a better approximation to this integral, and in fact a more Bayesian approach than the Bayesian approaches which are marginalizing within a single basin. So we're in practice, in real world, we're always handed computational constraints, and we try to do our best given those constraints. And deep ensembles is actually a very good heuristic for achieving a good approximation to this integral given those constraints. Here, we empirically test how close the deep ensembles predictive distribution is to a near exact predictive distribution, which we can see in panel A. In panel B, we have the deep ensembles. We can see visually it's fairly similar to the exact distribution. In panel C, we have a variational procedure doing single basin marginalization with a Gaussian approximate posterior. We can see that it doesn't capture epistemic uncertainty so well. It doesn't have a lot of uncertainty between different clusters of data points. The uncertainty doesn't grow very consistently away from the data. In the bottom right panel, we look at what happens as we, in terms of the distance between the approximate predictive distribution given by both deep ensembles and stochastic variational inference as we increase the number of samples we have access to. And we can see that that distance decreases very quickly for deep ensembles, but hardly at all as we increase the number of samples that we have with the variational procedure. So continuing to see samples within a single basin with this variational approach is not really improving our estimate of the Bayesian model average corresponding to this integral that we want to compute. But training more models in the deep ensembles is pretty dramatically decreasing the distance between our approximation and the exact answer. So in addition to just selecting different points in different basins, we can also try to marginalize within basins of attraction. And we do that in a procedure called MultiSWAG, where we train multiple independent SWAG methods discussed in part 3 to create a mixture of Gaussian's approximation to the posterior. So we're marginalizing within multiple basins. When we do that and apply MultiSWAG to several of the applications in reference 1, evaluating predictive uncertainty under dataset shift, which showed that deep ensembles often outperform single basin marginalization procedures, we see 2 key trends. One is that MultiSWAG tends to significantly outperform deep ensembles in cases where we're not training very many independent models or when there's a lot of data corruption. In purple here, we have an additional model, multi-SWA, which takes the means of the different Gaussian components in MultiSWAG, and that those will be in flatter regions of those different basins of attraction than say SGD solutions. And so we see a nice compromise here. Recently, a phenomenon called double descent has been of great interest. Belkin et al. A couple of years ago showed that we could find these so-called double descent curves on a wide range of problems where we have our loss on the vertical axis, and we can see as we increase model flexibility, initially loss appears to be decreasing, and then it increases corresponding to overfitting, and then it turns out it decreases again. And so this first regime is called the classical regime, which is in line with classical intuitions about generalization, and the next regime is referred to as the modern interpolating regime. So the training loss here just keeps going down. The test loss has this really non-monotonic behavior. And the question is, well, why don't we just keep overfitting? Why does suddenly generalization start getting better? especially once we move past where the training loss is 0. So I'd like to ask you, and feel free to pause the video for a moment, whether you think a Bayesian model should experience double descent, given what we've discussed so far. And considering this problem, especially think back to that first example at the beginning of the talk, where we're considering airline passenger numbers and which model we would want to fit that data with using a Bayesian approach. So in that airline passenger number examples, I was saying that if we have a reasonable prior and we're doing exhaustive marginalization, then we would expect a Bayesian method to improve monotonically with increases in flexibility. We should embrace flexibility, have large support. And indeed, that is actually what we see if we apply this MultiSWAG procedure. We see that performance is essentially monotonic, whereas SGD, in this example where we have CFAR 100, 20% label corruption, has a prominent double descent behavior. SWAG, where we're doing single Bayesian marginalization, has a less prominent double descent, but it's still clearly there. Another really important feature to note in this plot is the fact that MultiSWAG is actually just a lot more accurate than classical training. So if we have a ResNet with layers of width 20 here, we see just below 30% test error on CFAR 100, whereas if we're using SGD, we see about 45% test error. So it's a really massive discrepancy, and an empirical realization of this idea that if we're doing multimodal marginalization with a neural net, which can capture all sorts of complementary explanations to the data, then we're really going to benefit a lot empirically, not just in terms of uncertainty representation, but also in terms of accuracy. Now we'll consider the prior in function space that's induced by having a Gaussian prior in weight space, where we're just varying the signal variance of the prior for each of the parameters alpha squared. And so there are two key results that suggest that this actually induces a pretty reasonable prior in function space. First is the deep image prior, which showed that randomly initialized convnets without training provide excellent performance for image denoising, super resolution, and inpainting. In other words, a sample function from this induced distribution over functions captures low-level image statistics before any training. Another result from the paper by Zhang et al. On Rethinking Generalization shows that if we pre-process CFAR 10 with a randomly initialized untrained CNN, we get dramatically improved test performance when we're using a Gaussian kernel directly on pixels. So it goes from 54% accuracy to 71% accuracy. And then we just get another 2% from L2 regularization, which would be like tuning this alpha parameter. And so this is really saying that this induced distribution over functions is fairly reasonable. And in a way, it's not surprising, because the properties of the induced distribution over functions comes largely from the functional form of the model. That's really a big part of the prior translation equivariance in sort of a similarity metric that we get for different images, et cetera. This is going to come from mostly the functional form of the model. Now, in Bayesian deep learning, it's typical to consider what's called a tempered posterior, where we've raised the likelihood to a power 1 over t, where t is a temperature parameter. T less than 1 corresponds to a cold posterior, where the posterior is more concentrated around solutions with high likelihood. T equals 1 corresponds to the standard Bayesian posterior. T is greater than 1 corresponds to warm posteriors, where the prior effect is stronger and posterior collapse is slower. In a paper at this ICML by Wenzel et al., there's a result that's highlighted that with a standard Gaussian prior over parameters, cold posteriors often provide improved performance, but if we use just a temperature equals 1, we can get even worse performance than classical training. In this paper, they suggest the result is due to prior misspecification, and show here that sample functions from this induced distribution over functions with a standard normal prior seem to assign one label to most classes on CFAR 10, and we know the classes are balanced. So here we just sample from the standard normal, get our function with our neural nets, and we see that it's giving most of the data points class 6 here, and then another sample function is giving most of the data points class 9. We examine this behavior as we vary the scale of the prior variance on the parameters. So for alpha equals root 10, we reproduce this result, and we see that one sample function is assigning most of the data one class, another sample function most of the data the other class. However, if we reduce alpha, we see that the samples are very quickly assigning about the same amount of data to each of the classes. And in fact, of course, in practice, we would specify alpha through cross-validation or through, for example, just what we normally use for L2 regularization, which is roughly near 0.1 in this case. We also see that even for the misspecified alpha, the unconditional predictive distribution is actually quite reasonable. It's basically uniform over the different classes, so it doesn't affect the predictions. We can also examine the effect of data on the posterior here. So here we start with the prior, the misspecified prior, that this, where sample functions are assigning most of the data one class. We then observe just 10 data points with this huge ResNet, and we see that already the predictive, the samples are giving almost uniform predictions across the different points. 100 data points, even closer to uniform. And so this is a prior bias that is very quickly modulated by data. We can imagine with the Gaussian process, for instance, if we multiplied our kernel by some factor, the amplitude would be off. But if we observe, just a few data points, the posterior would quickly collapse in that region. So this is the kind of prior bias which isn't really going to affect generalization that much in practice. What's much more important, for example, is the induced covariance function that we get in this distribution over functions. And we saw this a bit in part 2, where things like covariance function really affected generalization. So here we have the induced correlation function for MNIST digits, different classes. We can see that the correlations generally decrease as we increase alpha. We also see that pretty consistently, the same classes are most correlated, and classes that are visually similar are more correlated than other classes. This is a good sign. This is also suggestive, in addition to the deep image prior and the random network features, that we're inducing a prior that is actually pretty reasonable. And which covariance function, for example, you use in a Gaussian process is going to affect generalization much, much more than whether you have a signal variance parameter that's a bit misspecified. So some thoughts on tempering. I think it would be very surprising if t equals 1 just happened to be the best setting of this hyperparameter. In fact, I think we should always be doing tempering. It's basically just an acknowledgement that our model is misspecified. That's not to say that we should, just say, well, who cares about the model specification? We'll correct it with tempering. We should do our very best to specify our prior as honestly as we can. But it's still going to be misspecified, and we should be honest about that too, and try to correct it by learning the temperature. And in fact, this isn't really too different than learning other properties of the likelihood, like noise. Now, while the prior P of x is certainly misspecified in most cases in Bayesian deep learning, the result of assigning one class to most data is really a soft prior bias, which 1 doesn't hurt the predictive distribution, 2 is easily corrected by appropriately setting the prior parameter variance alpha squared, and 3 is quickly modulated by data. What's much more important is this induced covariance function over images. In addition to not tuning alpha in this whole posteriors paper, the results could have been exacerbated due to lack of multimodal marginalization, which we've shown is extremely important for generalization. It's also interesting to note that there are cases when a cold posterior, a t less than 1, will be helpful in coming up with estimates, even if we believe the prior and the likelihood, if we have access to a finite number of samples. So we can imagine, for instance, estimating the mean of a standard normal distribution in high dimensions. In this case, the samples will be very concentrated around a norm of root d. And so if we decrease the temperature, we'll come up with a better estimate for the mean. And so I encourage you to try this. Just sample from a high d distribution, look at a histogram of the norms. So there was a paper a few years ago called Understanding Deep Learning Requires Rethinking Generalization. They showed that conv nets could fit CFAR with random labels, and this was presented as if it were in the face of everything we know about generalization, because it showed that the conv nets could fit in noise. They could greatly overfit, yet they were generalizing on all sorts of different problems. We can understand this result from the probabilistic function space perspective. So in the top row here, we have samples from a Gaussian process in panel A. In panel B, we see some structured data and a Gaussian process predictive distribution, which looks reasonable. In panel C, we see a lot of corrupted data in red, and we see an updated GP predictive distribution, which achieves 0 training error. Now, this red curve, unlike the green curve in panel B, looks nothing like the sample prior functions. However, the GP with the RBF kernel is very flexible. It contains somewhere in its support this red curve, even though we might have to sit there sampling for a very, very long time to see anything like it. However, if there's a strong enough likelihood signal, we're saying there's no noise, then it's going to run through that data perfectly and produce this predictive distribution. And so it doesn't want to fit that data, but it can. And we can quantify how much a model wants to fit data with something called the marginal likelihood. And so we can actually fit a Gaussian process on CFAR10 with altered labels and show that we get 0% training error. So that means that this result in the Rethinking Generalization paper wasn't unique to deep neural nets. You can reproduce it with Gaussian processes. And we can also compute the approximate marginal likelihood and show that it gets very, very low as we increase the number of altered labels. So that noisy CFAR set is somewhere in the tails of that distribution where we're considering all possible data sets and the marginal likelihood on the vertical axis when we're considering this GP model with an RBF kernel. We can also compute exactly the same thing using a Bayesian neural net, find the approximate marginal likelihood using Laplace, and we see that it decreases in the same way as we increase the number of altered labels. So this Bayesian neural net is able to fit that kind of data set, but it really doesn't want to. And we can quantify that with the marginal likelihood. And this is sort of in accordance with what we would want when we're thinking about model construction. We want large support, but we want to distribute that support carefully. And that means not giving a lot of mass to things like noisy CFAR. But if we see noisy CFAR, there's a strong likelihood signal and we can fit it. Okay, so of course, having said all that, the priors in function space aren't going to be perfect by just having sort of generic Gaussian distributions over parameters combined with functional forms of neural nets. And we can certainly do better. And I certainly embrace the function space perspective in constructing compelling priors for these neural nets. At the same time, we should be careful not to contrive priors over parameters W to induce distributions over functions that resemble familiar models, such as Gaussian processes with RBF kernels. We could be throwing the baby out with the bathwater in doing that. Indeed, neural nets are useful as their own model class precisely because they have different inductive biases from other models. We already have Gaussian processes with RBF kernels. And we can try to gain insights in thinking in function space, but this is, in a sense, what we're already doing when we're doing architecture design. That's thinking in function space, trying to encode properties such as translation equivariance, rotation equivariance, color and scale invariance, and other interesting properties that would induce a compelling similarity metric across our data instances. And so these properties really imbue the associated distribution over functions with desirable properties for generalization. And really all of the heavy lifting for the prior over functions that we get is from the architecture. And even if we're thinking more broadly, the functional formal model is like a strong prior. It's a very strong assumption. We can't escape assumptions, and we shouldn't try to. We should embrace assumptions. We need to make assumptions to have good generalization. PAC Bayes has been a very exciting approach for deriving explicit generalization error bounds in stochastic networks with posteriors Q, prior P, training points N. The PAC Bayes generalization error bounds are based on this term in equation 79, and we've recently people have derived non-vacuous bounds exploiting flatness in Q with at least 80% generalization accuracy predicted on binary MNIST. So this is very exciting. It's a promising framework, but it tends not to be prescriptive about model construction or informative for understanding why a model generalizes. So in a sense, it's very complementary to what we've been describing so far in this tutorial. And in fact, if we were to try to treat it as a prescription, what we would get is sort of almost contrary to a lot of what we've discussed. The bounds are improved by compact priors, for example. And we've been saying, well, we want priors with support for all sorts of different data sets. And a low-dimensional parameter space, in a sense, that the KL divergence is going to be often sort of hard to assign a lot of overlap between two high-dimensional distributions. And so we can very often achieve better bounds by doing model compression, et cetera. But here we've really been trying to embrace having as many parameters as possible for good generalization. Also, generalization, as we've shown, can be significantly improved by a multimodal posterior, especially in Bayesian deep learning. This is really one of the key practical takeaways. And in order to realize a good approximation to the unconditional predictive distribution, we really need to do multimodal marginalization. But the PAC Bayes generalization bounds aren't typically too influenced by multimodal posteriors. You end up with a log factor. It doesn't really change things that much. So the PAC Bayes bounds are quite complementary, and they're very exciting in the sense that they help us make sort of quantitative, explicit statements about generalization error bounds. But they don't tend to be too prescriptive. And this could be partly also because although we in some cases get non-vacuous bounds, they're also typically fairly loose. So what improves the bounds won't necessarily improve generalization. We can relate posterior contraction to a quantity called effective dimension and actually gain insights into behavior such as double descent. So effective dimension is of the Hessian here is the sum of lambda I over lambda I plus alpha, where alpha is a regularization parameter and lambda I are the eigenvalues of the Hessian. When we compute this quantity of networks, ResNets of varying width here, we can see that it tracks test loss very closely, as well as test error. And in fact, the effective dimension is going down as we increase the size of the models. And this suggests that actually we're getting simpler models, even though they have more parameters. We should be very careful not to treat parameter counting as a proxy for model complexity. And we can relate effective dimension to model compression. In a sense, this sort of counts the number of kind of sharp directions in this space given by the eigenvectors of the Hessian. And we can see that in this regime where we have basically zero training loss, all the different models are providing lossless compressions of the data. And so the best compression will capture the most regularity. It'll have this sort of Occam's razor property and tend to provide the best generalization. Now, the reason SGD finds these kinds of solutions when we make the model size bigger is largely because flat regions of the loss will occupy a much greater volume in high dimensions. And so SGD will be able to find them more easily. We also look at width-depth trade-offs, so looking at convnets of different widths and depths, and we can see above the green partition where we have zero training loss. Effective dimension is a very good proxy for generalization performance. The yellow curves here show level curves of constant numbers of parameters. It's interesting here especially to consider different depths. Typically, in recent years, we've been looking at infinite widths of neural nets for neural tangent kernels and things like this. But in a sense, depth is what gives deep learning a lot of useful hierarchical inductive biases that provides good generalization and representation learning. And so we can see that this quantity associated with posterior contraction in Bayesian deep learning is a reasonably good proxy for generalization. We can also look at the properties in function space as we move in directions given by eigenvectors of the Hessian with the smallest eigenvalues, and show that the decision boundaries are essentially unchanged, that we get a lot of functional homogeneity. And this provides a mechanism for why things like subspace inference, discussed in part 3 of the talk, work so well, why we can have a model with tens of millions of parameters and then basically just do marginalization in a 5-dimensional subspace and see a big difference for that. And so we can really understand things like model compression by looking at these quantities. In conclusion, what we've been really reiterating through this tutorial is that the key defining feature of Bayesian methods is marginalization, aka Bayesian model averaging, and that's going to be especially relevant in deep learning because neural nets are very underspecified by the data, contain all sorts of complementary and exciting solutions to a given problem, and it really makes a lot of sense just to use the sum and product rules of probability to marginalize those solutions. And really, in trying to do this marginalization as best as we can, we shouldn't think of the integration purely through the lens of simple Monte Carlo integration. We should probably think of it more as an active learning problem. And by doing that, we can gain insights into methods like deep ensembles and also propose other kind of Bayesian methods that provide even better marginalization, like MultiSWAG. And I'm very excited to say in the last year or so that a lot of Bayesian methods are now providing better results than classical training, both in terms of accuracy and uncertainty representation, without a lot of additional overhead. Really this emphasizes that there's a big difference between marginalization and just regularization, as we saw in that coin toss example. We should be careful not to conflate flexibility and complexity. Gaussian processes, for instance, can be extremely flexible, of an infinite number of parameters, simple inductive biases, good generalization on a small number of points, and also careful not to parameter count as a proxy for complexity. Sometimes the models with many more parameters, in a sense, are helping us find simpler solutions. And we can really resolve a lot of mysterious results in deep learning by thinking about model construction and generalization from a probabilistic perspective. So that's everything, and I really like to thank you for attending this tutorial. Thanks for attending the tutorial. I really had a lot of fun presenting and answering your questions so far. This is the last Q&A period. We have roughly 10 minutes, and then I've created another Zoom link which we can use to address potentially any further questions there might be. So yes, feel free to ask away. So there's a question in the Rocket chat asking to elaborate a bit more on the impact of varying the variance scale, slide 124. So this was in the context of our discussion about tempering. And the observation was that when we had a certain variance scale, so we put a Gaussian distribution over the parameters, P of W, zero mean, and covariance matrix alpha squared I, if alpha was sufficiently large, then sample prior functions that we would get when we sample from that distribution over parameters and then condition on those parameter settings and look at what functions we get in our neural net, tended to be assigning all the data points in CFAR 10 to one class. Now, I guess in this slide, we show that this is an artifact of that scale. Basically, the softmax just saturates very quickly, and we're kind of creating these high amplitude functions. And so in a way, that's what we would expect if we had a misspecified alpha. And if we change alpha, we can learn it through cross-validation, or we can just set it, for instance, to what we might use when we're doing L2 regularization. We don't see this anymore. We see that different sample functions are providing essentially sort of fairly uniform-looking distribution over different classes when we evaluate them on all the data points in this equally balanced problem. We also see that this aspect of the prior, where sample functions individually are assigning one class to all the points, is quickly modulated by data. So it's more of a soft prior bias. If we just observe 100 data points, then we see that this effect basically disappears. And even if we have the misspecified alpha, if we're looking at the marginal prior predictive distribution, so not looking at individual sample functions, but what happens when we marginalize over the sample functions, we do again have basically a uniform vote when we query on all the points. So it's not something that would really affect the predictions too much. So the point on this slide was basically that even though it seems dramatic to say that different sample functions are assigning the same class to all points, so a given sample function will assign the same class to all points on an equally balanced problem, this is actually a fairly soft prior bias, and it's very easy to correct. What really matters a lot more in terms of generalization performance and how the model is modulated with the addition of more data points is the kind of induced covariance functions. And we can think about this from somewhat of a Gaussian process perspective and say, well, what is this induced prior over functions that we get by having a fairly generic distribution over parameters combined with the neural architecture, saying about how different images are similar or different? If we translate an image, does it say it's a very related image? Certainly Euclidean distance would say that it's not. If we look at examples from the same class, a priori, do they seem to be correlated? And that's something that we consider a few slides further, I believe, slide 126. So that kind of thing is going to be much more important for generalization. And in a sense, as we mentioned a lot, especially in parts 2 and 4 of the tutorial, the prior that really matters is not the distribution over parameters in isolation. That actually has no meaning. It's the distribution over functions that we get. In the case of standard Bayesian neural nets, that's what happens when we combine the distribution over parameters with the functional form of the model. And so in terms of constructing a good prior, it's really, a question in many cases of architecture design. Is our prior going to say that translated images are similar or not? These kinds of things are really going to affect generalizations. So in a sense, the neural net itself is endowing the prior with a lot of interesting and kind of very important properties for generalization. Things like the scale of the prior over parameters is something that's more of a soft bias that's quickly modulated. We can also relate this to the Gaussian process part, where we could imagine multiplying the kernel by some value, and then the sample functions will be very high amplitude. But if we observe a few data points, we'll see that the posterior very quickly collapses because there's just a strong likelihood signal not to use that kind of amplitude. On the other hand, if we're looking at, say, the difference between using an RBF kernel versus another kind of kernel, like a Mathieurin kernel or a deep kernel or a spectral mixture kernel, we will see big differences in generalization behavior and how the model responds to the addition of more and more points. And so this is the kind of thing that I think we really want to think about quite carefully when we're considering, say, prior design. The complexity measure based on Hessian eigenvalues looks very interesting. Can you give some intuition for this complexity measure? This is from Burfin. The basic idea is that the effective dimension measures the number of kind of sharp directions in the loss surface. If you look at the eigen at a given solution, so if you look at the eigenspectrum of the Hessian of a trained neural net, interestingly, there tend to be two clusters. There's a small number of eigenvalues that are relatively large, and then everything else is very small. And the number of relatively large eigenvalues is essentially the effective dimension. And so this is actually quite an importantly different from other types of flatness measures, for example, that measure things like how the loss varies under random perturbations, etc. Those might be affected by, say, one really sharp direction. Also, the effective dimension is exactly related to posterior contraction. And so, we can get some interpretation from that relationship. Also, we can see that if we move in directions given by the eigenvectors with the lowest eigenvalues of the Hessian, there turns out to be a lot of functional homogeneity, which helps us understand why we can actually do things like subspace inference really effectively. If we move in those directions, we're not really changing the function space solutions even in test that much, so we can do a lot of compression. We can sort of interpret this also as vaguely the number of effective parameters in the model. So interestingly, as we increase the size of the model, we're actually finding solutions with a smaller number of effective parameters, simpler solutions. And intuitively, this is partly because in a high-dimensional parameter space, flat regions occupy a much greater volume, so they're actually more easily discoverable. Now, also, as we saw when we're doing full Bayesian marginalization, and we're trying to do a really good job of exhaustive marginalization, like multimodal marginalization, we actually see that things like double descents disappear. And we can embrace this perspective essentially on slide 1 of this tutorial, where we're saying, let's use the 10,000th order polynomial. In fact, let's use an infinite order polynomial. If we can manage it, we should basically expect performance to be monotonically improving with flexibility, as long as we're also honestly representing our beliefs in the modeling procedure. And that means trying to do a really good job of marginalization and trying to be reasonable in prior specification. Thanks for attending the tutorial. Welcome to the Zoom Q&A, where I'm happy to answer any questions you might have at this point. There are also a couple questions in the Rocket chat that I can address. So if you have a question, feel free to ask either in the Rocket chat or in the Zoom chat. I'll read it out and we'll discuss it. So in part 2 of the tutorial, we discussed this quote from David McKay, where he says, how can Gaussian processes replace neural nets? Wouldn't we be throwing the baby out with the bathwater in doing that? And Alex Shim asked an interesting question. So he tracked down the chapter in that edited book about neural nets and found some additional remarks that were made where Mackay says that evidence that this infinite limit has lost something compared with finite neural nets comes from the observation that in a finite neural net with more than one output, there are non-trivial correlations between the outputs, but in a limit of an infinite number of hidden units, these correlations vanish. So this observation was also made by Radford Neal in his 1996 PhD thesis when he derived this limit, which triggered a lot of interest in Gaussian processes in the ML community. And he also says maybe it was the wrong limit to take. And recently, a number of works have been pursuing other types of limits of infinite neural nets, although many of them still give rise to kind of a fixed kernel representation. So the fact that the subsequent layers would become uncorrelated and the different outputs would become uncorrelated suggests that they're no longer, that the outputs in the later layers are no longer sharing sort of a hidden representation from the previous layers, which is really the power, in a sense, of a neural net. We have this hierarchical representation learning that's happening through multiple layers. And if we're thinking about the neural net as a multitask model, in a sense, where each output could be a different task, then the different tasks would be correlated because they all have these hidden basis functions which are learned. And so that would be one way of seeing that we have potentially lost something in taking the infinite limit, at least the way that it was taken in the early work. We can regain what's been lost by developing kernels which can discover these interesting hidden representations. And so if the kernels are structured, for example, by a multi-layer neural net as they are in deep kernel learning, then we can, again, discover these interesting hidden representations. There are also kernel learning approaches that aren't based on neural nets, like spectral mixture kernels and functional kernel learning, which was at NeurIPS last year, which discover pretty expressive hidden representations that wouldn't have been possible using a fixed kernel function. And so deep kernels, as well as spectral mixture kernels and several other kernel learning approaches, can get around this criticism through discovering this sort of similarity metric, which is, in a sense, what we're getting through learning multiple layers in a neural net. At the very end of a neural net, you could typically see almost like a linear classifier, for instance. And so one perspective on deep learning is to basically view neural nets as learning a transformation such that your problem is then linearly separable, or is quite simple in some sense, where things like Euclidean distance make sense again. So that's the sense in which deep kernels and other kernel learning approaches can get around this remark. So we have a question: what exactly do you mean in the conclusion saying that seeing marginalization through the MC lens might be a bad idea? Right, so this is an important question. I guess in practice, it's very common to compute the Bayesian model average by sampling from some kind of approximate posterior and then averaging the conditional predictive distributions associated with those parameter samples. I would argue that in many cases, we can often provide a better estimate of this integral that we're trying to compute with this Bayesian model average by not doing this simple Monte Carlo procedure and instead thinking of the integration more as an active learning problem under constraints. So deep ensembles, I think, is a good example of a method that does this. So there have been a number of papers suggesting that the deep ensembles outperform various Bayesian methods, especially single basin marginalization approaches. And the suggestion of, well, maybe we should just move towards ensembling it, and there's a sense that this is non-Bayesian. And in the paper, Bayesian deep learning and a probabilistic perspective of generalization, we argue that, in fact, if we're conditioning on computational constraints, like there's a certain amount of computation we want to expend on our procedure that's finite, then deep ensembles is actually a pretty good active learning style heuristic for approximating this integral, which is really fundamentally what we want to estimate, because it's selecting for functional diversity through finding different basins of attraction. And sometimes if we're just taking posterior samples, we're not actually going to be getting functional diversity, or we might have to sample for a very long time to start to get a good estimate of this integral. And so I think that a lot of procedures like deep ensembles start to make much more sense when we move away from this simple Monte Carlo perspective of estimating the integral. So this is different than, say, MCMC. MCMC samples are often used as simple Monte Carlo, but simple Monte Carlo is just often, how we use samples that we get from some approximate posterior, whether it's from MCMC or some deterministic approximation. And MultiSWAG in the last part builds on this observation that by incorporating different basins of attraction, we'll be able to come up with a much better estimate of this integral that we want to compute. And so from this perspective, getting samples from a posterior, or even having a high fidelity representation of the posterior in some region, might not be that crucial if our goal is really just to come up with a good approximation to this integral under computational constraints. And so I think an exciting future direction, will include trying to think of active learning approaches to consider where we want to query our posterior next, or where we want to move in parameter space next, and evaluating our conditional predictive distribution in order to provide the biggest gain in our Bayesian model average. And there were some figures we showed briefly in the last part, which consider this question in a sense: where would we move in parameter space to decrease the Wasserstein divergence between the true model average and our approximation the most? Well, that's a nice question. The log model evidence of a GP seems to be unbounded from below. Would it be possible for SGD to know when to stop when it is richly parametrized by an NN kernel? So with deep kernel learning, we have, in regression at least, often an exact marginal likelihood. And we would estimate it in a similar way to how we would, estimate standard objective for training the model, with the caveat that the marginal likelihood for not using, say, a variational approximation typically doesn't factorize the way that a standard neural net training objective would. The benefit of the marginal likelihood objective is that it compartmentalizes nicely into a model fit term and an automatic complexity penalty given by the log determinant question. And given log determinant complexity penalty, which is sort of this Occam's factor. And this will provide nice automatic calibration, which is quite different from, say, regularized optimization, where we have to come up with maybe an ad hoc sort of complexity penalty. This is a penalty that we get through marginalization. There is an in practice sort of difficulty in knowing when to stop. Typically, we just optimize to convergence, and in practice, we often find we get a good solution. One could take the approach a step further and put a distribution over parameters in a deep kernel and try to marginalize those parameters as well. Historically, that hasn't been done so much because until recently, maybe in the last year or two, it's just been very, very difficult to try to marginalize all the parameters in a neural net. But a lot has changed, and now we're coming up with reasonably good approximations, or approximations that provide pretty significant practical benefits over classical SGD training. And so now I think it would be possible to do both, although it's unclear, it's kind of an open question how much it would help beyond the standard deep kernel learning approach, because we are still integrating away this whole non-parametric distribution over functions in the deep kernel learning approach. And in practice, I found that the credible sets tend to be pretty reliable, although we might expect them to be slightly overconfident because we are conditioning on those kernel hyperparameters being known. Okay. Right, so we have a question about whether it might be possible to have MC dropout converge to different basins of attraction for different parts of weight space, like MultiSWAG and deep ensembles. So that could be very possible. I think the simplest approach would be to just run multiple independent MC dropout methods. So basically just have a bunch of parallel kind of MC dropout chains going and combine them together at the end. And you would achieve sort of benefits like deep ensembles. And I would expect that potentially to work a bit better than standard deep ensembles. You could also do something similar with, say, variational methods. You could run multiple variational approaches and get multiple Gaussian approximations. MultiSWAG is particularly convenient because we basically just recycle geometric information in standard SGD training to get a fast approximate posterior, and then we can sample from that. And so we can, in MultiSWAG, we can sample from this mixture of Gaussians posterior, and it's just, yeah, very convenient with essentially no additional computational expense at training time. But you know, running multiple other types of single basin approaches with different initializations could, in some cases, help us also provide a multimodal characterization of the posterior, which it turns out is very important in deep learning. And it's something that might distinguish Bayesian deep learning somewhat from a lot of other applications of Bayesian inference. So if we're looking at logistic regression or other types of models, often the posterior is pretty close to Gaussian. And so questions of multimodal marginalization and so on don't come up as much in those other settings. Whereas in Bayesian deep learning, it seems to be practically crucial. So there's a question about whether we could modify the inductive biases of the deep neural network through kernel specification to find qualitatively different types of solutions. And I think this is actually quite an interesting idea. In the deep kernel learning paper, we showed that using different base kernels could lead to quite different performance. And for example, you start with this base kernel, like an RBF kernel or a spectral mixture kernel, for instance, and then you transform the inputs of those kernels with a neural net, and then you learn all the parameters of the resulting deep kernel through the marginal likelihood of the GP. But we found in the paper on deep kernel learning that when we used the spectral mixture kernel, we were capturing, you know, interesting frequencies in the feature space of the neural net that we would have been missing with an RBF-based kernel. And so I think that, you know, this is a nice way of sort of getting some of the inductive biases of a deep neural net, but also modifying them through a base kernel. And that's a relatively unexplored direction that I think could be quite interesting. So we had a question earlier. Many people have claimed that the Bayesian framework is more robust against corrupted or noisy labels compared to point estimate methods, maximum likelihood, or MAP. Could you please give some comments? So that does tend to be true. And in fact, in the double descent experiments, we saw that performing more exhaustive marginalization both mitigated double descent quite significantly and also provided pretty significant gains in accuracy. And in a sense, we could view double descent as an artifact of overfitting. Basically, our generalization performance improves as we increase model flexibility, and then we start to overfit as we continue to increase the number of parameters of the model, for instance. And then it sort of begins to improve again. And this last regime, the modern interpolation regime, has been treated sometimes as quite mysterious because we might naively expect the model to continue to overfit more and more substantially as we increase the number of parameters, potentially the flexibility. And we could sort of view that, you know, Bayesian methods as mitigating double descent by, you know, in a sense sort of reducing overfitting. And we also see that double descent is actually more prominent when we introduce label noise. And so this again suggests that it has sort of something to do with overfitting, and this is something that can be mitigated by a Bayesian approach. We also saw in the last part, when we compared MultiSWAG with deep ensembles, the largest practical benefits occurred when we were either in a regime with a lot of data corruption or in a regime where we didn't have that many models to include in the ensemble independently trained models. And so marginalizing within the few basins that we do have access to became especially important. So I would say that that's reasonable, and the intuition for why these model averaging approaches could be much better than, say, regularized maximum likelihood or MAP in those settings is because I think when we have a lot of noise, you're going to tend to see more disagreement between models in the average, and that's when we're going to tend to benefit the most from a Bayesian model average or an ensembling like approach. Whereas if the models are all pretty much in agreement, then we're not going to see as much of a benefit compared to classical approaches, and they'll tend to be more in agreement if the data is kind of simple and more noise free. So that's why you tend to get more robustness against noisy labels. And maybe the short answer is, we are helped against overfitting when we follow a Bayesian approach, and that's through model combination. So there was a question about estimating aleatoric uncertainty. The question says, it doesn't seem wrong to say uncertainty equals epistemic plus aleatoric. You've discussed how the posterior predictive distribution accounts for epistemic uncertainty, but I suppose my main reservation is that the estimates of epistemic uncertainty will still depend on the types of model that one decided to include in the prior. So that's certainly true, and I would argue as a prescription for model construction that we should try to have quite broad priors so that we're not ruling out solutions that we believe might be possible. Now, it's okay if we don't believe those solutions are probable, because we're not sort of, when we're talking about support, we're just talking about which models we want to include. When we're talking about inductive biases, we're talking about which models we think might be a priori likely. And so we'll have to consider both very carefully in model construction, but typically we want large support because we don't want to rule out things that we think are possible, even if we think they're improbable. And in terms of aleatoric versus epistemic uncertainty, so in many cases, aleatoric, the sort of unreducible uncertainty, is it sort of manifests itself as noise when we're looking at these data points, and we should be estimating noise, I think. So this is sort of like estimating a property of the likelihood, and we can see that sometimes there's a bit of a trade-off between the two, and how that trade-off is managed will depend on how we specify our likelihood in prior and the inductive biases of our model. I think that estimating aleatoric uncertainty and noise also has a relationship with procedures like temperature scaling, where we raise our likelihood to a power 1 over t, where t is a temperature. In a sense, trying to learn a temperature or find a reasonable value of a temperature is like learning a property of our likelihood, which is like learning noise, especially in the regression setting, which is in a sense like trying to manage aleatoric uncertainty. So I think we should be trying to model both for sure. And I think Bayesian methods generally do attempt to try to capture both types of uncertainty. That's a good question. So there was a question about how to select good priors for Bayesian models. It might take a couple of years to answer this question in full, but I think that one nice way of getting some intuition for priors is to try to convert parameter space to function space as best we can. So a common way of trying to do that is to sample from the parameter prior and then condition on the value of the sample that we get and take a look at what our function appears to be doing when using those parameters. And we can just keep repeating that procedure and try to visualize the induced distribution over functions. This, of course, can be difficult when we have, for example, a high-dimensional input space, we might want to try to visualize in a few directions, or we might want to start looking at things like induced covariance functions in the prior, which is something we did in the last part when we were looking at the priors that we sort of induce with generic distributions over parameters in Bayesian neural nets. And from that perspective, prior construction really revolves a lot around architecture design. And so in a way, a lot has been done for us just through the development of convolutional neural networks and other types of architectures which have properties like translation equivariance, this idea that if we translate an image, for instance, that its class label might be unchanged. And so I think we can build better priors largely through building better architectures. And we should be very careful never to just think about priors as distributions over parameters in isolation, because in all cases, the prior that matters is the prior over functions, not the prior over parameters. The prior over parameters actually just means nothing in isolation. And so, I would say generally, think in function space, and don't think that if you have, say, a vague distribution over parameters, that you somehow have a vague prior, because you probably won't have a vague distribution over functions. And if you did, then that might be problematic because your inductive biases might not be very well calibrated. So there's a question about how the curve subspace is constructed. So I mentioned in the tutorial that I became quite interested in Bayesian deep learning after seeing this figure explaining why mini-batch SGD might find flat regions of the loss and how that could have consequences for Bayesian model averaging in particular. And this triggered sort of initially an exploration of some of the topological properties of the loss surface. And so in this work called Loss Surfaces, Mode Connectivity and Fast Ensembling of Deep Nets, we showed that there were these connecting subspaces, and we found them by first training a neural network twice with, say, different random initializations, just like we might do if we were forming a deep ensemble, and then introducing a parametric curve, which has as its endpoints those two solutions, and then learning the parameters of that parametric curve by minimizing the loss that we use to find the endpoints uniformly in expectation over the curve. So if the curve is sort of one-dimensional, then this would look like a line integral of, for example, cross entropy normalized by arc length. And it turns out this is a fairly easy thing to optimize, and we found that we could always find these subspaces as long as we didn't use a direct linear path. So we could go as simple as just a polygonal chain with a single bend, which is like 2 line segments. But direct linear paths always seem to incur quite a large amount of loss between the solutions, which is probably why historically we viewed these different solutions as being isolated, but it turns out that they're not. And in fact, we can find directions which along which the loss is extremely flat, and we can walk from one solution to another. So that's how we constructed those subspaces. And there's further detail on the paper if you'd like to read more about it. So there's a question about capturing modes of the posterior sequentially versus procedures like deep ensembles, which find different modes through random independent initializations. It's an interesting question. I'm not sure exactly what you mean by sequentially, but potentially you mean sort of like the cyclical learning rate or a cyclical MCMC or something like this. I think that one of the advantages of starting with random independent initializations is often ending up with greater functional diversity in the ensemble. Whereas if you're taking steps with, say, a cyclical procedure, you get some diversity, but not quite as much. So if you have the same number of models in your ensemble with that approach, you probably won't do quite as well as if you do a bunch of independent training runs. On the other hand, a bunch of independent training runs will be a lot more expensive. So if we condition on the same amount of computation, capturing modes sort of sequentially in a sense, might actually be a lot more fruitful. My guess is some sort of mixture of the two approaches is probably practically optimal. So having, for example, multiple chains and each of them with cyclical rates, and the two procedures will probably complement each other reasonably well. That said, there are probably many different parameter settings which provide diverse and compelling explanations that aren't easily reachable through standard kinds of SGD procedures. And so it's kind of an open question. Once you have retrained your model, say 10 times with deep ensembles, there appear to be pretty greatly diminishing returns in continuing to retrain an ensemble. And so I think that we could probably still do a lot better by thinking of other ways we could access interesting and different solutions, which might not be easily found in the subspace that SGD itself is exploring when we run SGD. All right, so that will be the end of the live Q&A. Thanks so much for all of your questions. If I missed something, feel free to just ping me on Rocket Chat or email, and I'll try to follow up. I really appreciate you coming to the tutorial. It's really been a fun experience, and I hope you enjoy the rest of ICML.